Okay, here we go. I'd like to give you a little support on trying out these problems today. These problems are all about this idea of mechanical advantage. And as we just talked about, that is simply a measure of how much easier a machine makes the work. Remember, machines make work easier usually by changing the amount of force that we need. So as you notice here, we're going to use a couple things that are familiar. We're going to use the relationship we've been using for work even more. Remember that work is the product of force and distance. So as we think about using a machine and it changes how much force you need to use, the ratio of force out and force in is going to tell us how much easier. If you think back to the lab last week, we were lifting a 10 Newton weight with a pulley system. And in one of the trials, it took about 5 Newtons to lift. If it only takes 5 Newtons to lift a 10 Newton weight, hey, that's an advantage, isn't it? The output force in that situation was 10 Newtons, but the input that we had to use was only half of that. I only had to use about 5 Newtons of input. Notice 10 over 5 is 2. And what that means is the mechanical advantage is simply 2. Now, an interesting thing to note about that, you notice it's not 2 Newtons. It's not 2 anything. In fact, the Newtons go away. On the top and on the bottom is the unit Newtons. So just like a number, those two cancel out. So when we talk about mechanical advantage, in fact, there are no units for this number. It's just the number of times the machine makes work easier. There's a discussion about that on this sheet, and I'd like you to give that a read today. It talks about it right here, how the force is present in the denominator and the numerator, but as a result, it cancels out. So as you're thinking about using forces to calculate mechanical advantage, there are a couple of problems here that I want you to look at as practices. And today, your job will be simply to try the first set of problems on page 2. We'll come on tomorrow and try some other ones. But today we're going to think just in general about mechanical advantage. So as you see here, again, a discussion about how mechanical advantage tells you that machines make work easier. Usually, that easier means the force gets bigger. And again, here's an example of a force of 200 Newtons input and a 1,000 Newtons output. As you can guess, 1,000 Newtons is 5 times bigger than 200 Newtons. So here we calculate force out divided by force in, and we come up with a mechanical advantage of 5. Notice again, there's no unit on the 5 because the Newtons over here cancel out. So that just means that particular machine makes work 5 times easier. That's pretty typical for a machine to do that and have a mechanical advantage bigger than 1. And that's not always the case. Usually that's the case, but that's not always the case. So take a look at another example. Example number 2, again, you can read these, talks about a different kind of machine. Now, this is a machine where, gosh, something turns out to be different. Now, we make it work a little bit harder because we don't give you quite the same amount of information. Now, we give you the input force, 30 Newtons. So that's force in. And you know that the machine lifts through 10 meters. That means that's distance in. And then you see the machine is designed to lift an object to a height of 2 meters. So that's the output distance. That's the job the machine does, distance out. And you'll also notice that it says here the total work output for the machine is 18 Newton meters. A little bit trickier. We don't know in this case what the MA is. You know, to find MA, we need force out and force in. Well, we already have the force in, but we don't have the force out. But here's the catch. We do know the work out, and we know the work out is equal to force times distance, just like usual. I'm going to write a little O there, force out times distance out. And because we happen to know these numbers, that means we know that 18 Newton meters is equal to the force out, which we don't know, that's what we're trying to find, times the distance out, which we do know is 2 meters. So what you need to do is use your work expression first to figure out what the force is, and then we're set. As I think you can imagine, we can solve this right here by dividing both sides by 2 meters. All right, we divide by 2 meters here, divide by 2 meters here, And what you find out, 18 over 2, of course, is 9. Notice the meters both cancel and we get newtons. And the force out is 9 newtons. And of course, once we know that, now we're all set. We can go ahead and use that to find the mechanical advantage. So this is, in fact, a two-stepper. But again, here's that same calculation. We come up with the 9 newtons. Now we know the original 30 newtons and the 9 newtons. And gosh, 9 over 30, look at this. We have a mechanical advantage less than 1. Strange. But you know what? Once in a while, that's useful. You'll see some examples here of machines where the force you put in actually gets smaller, but the goal is that the distance gets bigger. Once in a while, that's useful. Think about a bicycle. You turn the crank on the wheel or the crank on the pedal of a bicycle a small distance, and the back wheel goes through a really big distance, and it makes you go a long ways. Once in a while, machines have mechanical advantages smaller than 1. Anyhow, that being said, what I'd like you to do today is use those skills and practice through these problems. There are 5 problems here. This is page 2 of the mechanical advantage problems. The work is what you really need to show. As you know, we have the answers posted for you to check out today, but I want you to try these problems. Pop into office hours if you have questions. Give us a shout, but give these a try, and then tomorrow we'll come back and work on the balance of them. Thanks, folks. Have a great day.